Welcome to the technical seminar in thermal analysis. My name is Lani Celis and I will be your presenter. Today's topic focuses mainly on metals, ceramics, and other materials using simultaneous thermal analysis or STA, differential scanning calorimetry or DSC, and evolved gas analysis or EGA methods. The International Confederation for Thermal Analysis and Calorimetry defines thermal analysis as a group of techniques in which a property of a sample is monitored against time or temperature while the temperature of a sample in a specified atmosphere is programmed. The physical properties evaluated by thermal analysis and their appropriate techniques are listed on this table. For changes in mass and the temperature difference between a sample and a reference material, the simultaneous thermal analysis or STA, composed of thermogravimetry and differential thermal analysis method is used. For quantifying the energy in a reaction, the differential scanning calorimetry or DSC method is utilized. For qualitative identification or quantitative characterization of gases in a mass loss reaction, the evolved gas analysis or EGA technique is utilized. Here is an illustration of a TG curve indicating mass loss and mass increase, and how the common reactions are represented in a DTA or DSC curve, which are both plotted against temperature. By combining both TG and DTA or DSC, we can elucidate reactions such as the reactions listed on the table on the right side of this slide. Reactions such as melting, crystallization, glass transition, phase transition, dehydration can be measured by both STA and DSC. Other reactions such as decomposition, evaporation, sublimation, or water vapor absorption are recommended to be analyzed by STA. With the Rigaku Thermoplus EVO2, a maximum of 8 thermal analyzers can be controlled by a single Thermoplus EVO2 PC station using the measurement software and analysis software. As shown in our example, the PC is connected to a DSC with a refrigerator cooling unit that has a temperature range from -90 up to 725 degrees centigrade, an STA with a sample observation camera that allows simultaneous measurements with captured images, a high temperature type DSC, evolved gas analysis systems, and a TMA instrument. From this slide onwards, we will be discussing about differential scanning calorimetry or DSC. So differential scanning calorimetry or DSC is an indispensable tool that corresponds to a wide range of materials for the quantification of the amount of energy in a reaction. This slide shows us an example of a DSC data plotted against temperature. From the DSC curve, we can observe a baseline shift due to glass transition commonly found in semicrystalline materials, while an upward peak indicates exothermic reaction due to the release of heat from a material, and a downward peak reveals endothermic reaction due to the absorption of thermal energy. The energy of these reactions are quantified and expressed in joules per gram. The applications that we will be discussing are structural transition in quartz, Curie point of lithium niobate by high temperature DSC, and we will introduce to you the sample observation DSC. Quartz is an important mineral in most industries. Here is a DSC application on quartz, where we can observe an endothermic peak at 571 degrees centigrade, revealing structural transition from alpha form to beta form. DSC is also used in the evaluation of Curie temperature, which is an important parameter for the design of ferroelectric devices. Curie temperature is a second-order phase transition in which a material in a ferroelectric state changes into a paraelectric state. Here is a measurement result using high-temperature DSC of a 50 mg lithium niobate. In DSC, the baseline gradually changes in the endothermic direction up to 1133 degrees centigrade and suddenly shifts in the exothermic direction at 1133 degrees centigrade. The second-order phase transition is a change in heat capacity, which is seen as a Curie temperature. This thermal behavior should be observed as a baseline change rather than an endothermic peak. For decades, we learned about the fundamentals of thermal analysis and thermal behaviors of materials. However, we cannot imagine the visual changes such as change in color, volume, loss of shape in a material as it undergoes a reaction. Recently, the use of sample observation camera in obtaining the actual images on the visual changes in a material associated with thermal behaviors is increasingly becoming significant because it provides new knowledge and information by direct observation. Here is an application showing the phase transition of azoxyanisole by sample observation DSC. This was measured from room temperature up to 150 degrees centigrade and cooled down back to room temperature. As the temperature changes, notice a change in color as the material goes through phase transitions. Through the sample observation option, we can attach the captured images in each temperature in writing reports and save them in PDF format. Also, we can create a movie on the measured data and save them in an MP4 format or Windows Media Video format as shown in the next slide. Here is the slideshow saved in a video format of the phase transitions of azoxyanisole by sample observation DSC. Initially, the sample is at liquid crystal phase 3. Notice a change in color and state during heating as it changes to liquid crystal phase 2 during the first endothermic reaction, and another change in color when it changes to liquid crystal phase 1. So during the cooling process, we can see exothermic reactions and changes in color as the material goes back to the liquid crystal phase 3, which is the same as the initial state. From this slide onwards, we will be discussing about simultaneous thermal analysis or STA. The STA technique is a simultaneous method composed of thermogravimetry or TG, as shown in green curve, which measures the mass change of a material as a function of temperature or time. On the other hand, the differential thermal analysis or DTA, as shown in blue curve, measures the temperature difference between a sample and the reference material as a function of temperature or time. This example is a measurement result of calcium oxalate monohydrate, a standard material for TG method, which was measured in air atmosphere. The first mass loss is dehydration, revealed as endothermic reaction. Then in the second mass loss is the formation of calcium carbonate and an evolution of carbon monoxide. And since this is measured in air atmosphere, the oxygen is present and combustion of carbon monoxide to carbon dioxide occurs that produces the exothermic effect. Then in the final mass loss, calcium oxide is formed and carbon dioxide is evolved from the decomposition of calcium carbonate, which accounts for the endothermic reaction. Therefore, by combining both TG and DTA or DSC, we can estimate the kind of reaction in a material. This is an STA measurement of palladium powder measured in air atmosphere from room temperature up to 1000 degrees centigrade. Near 390 degrees centigrade, we can observe a mass increase of 11.9% associated with exothermic reaction due to oxidation. Then as the temperature increases, the DTA shows endothermic reaction near 849 degrees centigrade, and the TG curve shows a mass loss of 14.3% due to reduction. Notice that the mass loss due to reduction is higher than the mass increase due to oxidation by 2.4%. This suggests that the palladium powder was initially oxidized before the measurement, and at the end of the STA measurement, a pure palladium powder was obtained. The STA technique is also advantageous in measurements where we compare treatments, such as the application shown in this slide. Here, we compare the aging difference of a material by STA on carbonation of calcium hydroxide. The fresh sample, or the original sample shown in blue curve, shows a mass loss of 23% at 410 degrees centigrade with an endothermic peak due to dehydration. On the other hand, the sample kept at 25 degrees 60% relative humidity for 7 days, as shown in the red curve, allowed the sample to absorb carbon dioxide from the air atmosphere, and that a part of calcium hydroxide has changed to calcium carbonate, which resulted to low percentage of dehydration at 410. While the mass loss at 600 degrees centigrade is due to the carbonation of calcium carbonate. STA is also an effective tool in confirming the thermal behavior of a binder in a battery material and its debinding process during firing. This is an STA result of an unfired anode material. The DTA result reveals the melting of the added binder at 99 degrees centigrade and at 142 degrees centigrade. As the temperature increases, we can observe a mass loss at 300 degrees centigrade due to thermal decomposition of the binder. Here, the STA result indicates that the added binder amount is 19.5%. Here is a typical result of cement. The green curve is a TG, and the black curve is the derivative TG, which shows the mass loss rate of cement. All of these curves are plotted against temperature. This result shows a 4-stage mass loss starting near room temperature up to 800 degrees centigrade. The reactions on the first 2 mass losses accounts for a complicated dehydration reaction process, while the 3rd stage and the 4th stage mass losses are due to dehydration of calcium hydroxide, which is 0.2%, and decarbonation of calcium carbonate with a mass loss of 0.85%. Now let's analyze the complicated dehydration behavior of the first 2 mass losses. Looking at the TG and the DTG curves from room temperature up to 300 degrees centigrade, we can see 2 poorly resolved peaks on the DTG. Based on this DTG curve, if the TG curve is divided into 2 reaction stages, then the mass loss percent can be analyzed. It could be estimated that the first stage is 0.34% and that the second stage is 0.09%. However, the 2 stages are not clear because they occur in an overlapping continuous manner. Regarding a technical method of separating overlapped dehydration reactions, there is a technique that uses a self-generated atmosphere effect. For example, by using a quasi-sealed container with a small pinhole on the lid of a sealed pan, the rate at which the evolved gas is released to the outside of the sample pan can be controlled. In this case, each dehydration reaction that occurs continuously in the sample pan is suppressed by the self-generated water vapor and can be observed as 2 separated reactions. The left graph shows the STA results of gypsum dihydrate using the self-generated atmosphere of the pinhole pen. From this result, first, gypsum dihydrate dehydrates 1.5 water molecules to produce semi-hydrated gypsum, and followed continuously by the dehydration of 0.5 water molecules to produce anhydrous gypsum. Summarizing the above results, it was concluded that gypsum dihydrate is contained in the cement from overlapping reactions in the first two stages of mass losses, and that the evolution of sulfur dioxide from 800 degrees centigrade is observed. From the results of the previous slide, using the mass loss percent on the TG curve obtained from the theoretical mass loss of the dehydration and decomposition reactions of calcium hydroxide, calcium carbonate, and gypsum dihydrate, the content of each of these compounds in the cement can be finally estimated. Recently, the use of sample observation technology has increasingly becoming popular in the field of thermal analysis. Using this attachment, the physical changes such as change in color, shape, volume can be confirmed visually, providing additional information and accurate description of the obtained reactions. Our next application is approximate analysis of coal using STA as specified in ASTM conditions. Conventional method in proximate analysis involves a series of measurements and is usually tedious and time-consuming. However, the STA method is an alternative method where it can quantify the moisture content, amount of volatile products, total carbon content, and ash content in a single measurement. First, the coal is heated under inert atmosphere at a constant heating rate up to 100 degrees centigrade and is held constant for the dehydration reaction. Then the coal sample is heated at a constant heating rate up to 950 degrees centigrade and the temperature is held constant for the removal of volatiles or thermal decomposition reaction. Then the atmosphere is switched from inert atmosphere to air atmosphere for combustion of carbon. Finally, the residues after the combustion reaction will be the ash content. This slide shows the configuration of the sample observation STA attached with a mass flow unit during the measurement of coal. The mass flow unit is used in measurements when gases are switched automatically from inert gas atmosphere to air atmosphere. Here, the user can set the flow rate and the timing of automatic gas switching in the temperature program. This slide shows us the video by sample observation camera on the proximate analysis of coal in STA. The first mass loss is due to dehydration when it was heated. Here, we cannot see any changes on the sample. The next stage is due to thermal decomposition when it was heated up to 950 degrees centigrade. Here on the camera, we can clearly observe a volumetric change in sample size during thermal decomposition reaction. The third mass loss is due to combustion of carbon content when the atmosphere was changed to air. During combustion, the sample color changed from black to light gray. Finally, the residue is the ash content, which can be calculated from the TG measurement result. With the sample observation camera option, the user can write a report with captured images attached on thermal events that are significant to the results of a measurement, providing a more detailed description on the visual changes of the sample. Here is another application on sample observation STA on cobalt sulfate heptahydrate. It was measured from room temperature up to 350 degrees centigrade. Here we can observe several mass losses with endothermic reactions. All these reactions are due to dehydration reactions that exhibit different visual changes in color and in volume on the cobalt sulfate heptahydrate. With a sample observation camera, the user can create a movie on the measurement result showing the original image of the sample and comparing it with the significant changes occurring in the sample as it goes through dehydration reactions during heating. The photo on the left side is a sample image at 26 degrees centigrade. So now we can see the volumetric change in size. So there is the shrinkage. And after that, as we go through the third mass loss near 200 degrees centigrade, we can observe another change in color and in volume to darker purple. Up to the end of the measurement. From this slide onwards, we will be talking about evolved gas analysis or STAMS. This is a slide I have shown earlier. Reactions such as dehydration, evaporation, decomposition, sublimation, or combustion are common reactions where there is a mass loss, and if there is a mass loss, then there is a simultaneous evolution of gases. Using the evolved gas analysis or EGA technique, we are able to qualitatively and quantitatively analyze evolved gases. Through this, we can understand the kind of gases and their evolution behavior. An EGA system is divided into three major components. First, the sample is heated in STA for gases to evolve. Then the interface transports the evolved gases without condensation, and finally, the MS or FTIR detects the gases qualitatively. This is an example of an EGA measurement result. Here, the EGA curve is added to the STA data, all plotted against temperature, represented in the black curve, where peaks indicate detection of evolved gases. A gas detector system can be an MS or an FTIR system. If the gas detector is an MS system, the total ion current or TIC curve is the sum of evolved gases detected as ions with relative abundances plotted against time or temperature. We can extract the mass spectrum in each temperature and compare it with a database library for identification. The debinding process of commercially supplied alumina ceramics sheet was measured in inert atmosphere by electron ionization or EI mode and photoionization or PI mode. EI mode is used for the detection of organic gases, inorganic gases, and their fragmentation ions. PI mode is used for the detection of molecular ions that are derived from organic gases that has an ionization potential of less than 10.2 electron volt. Our results show that mass loss is observed between 350 degrees centigrade up to 500 degrees centigrade associated with evolved gases. EIMS shows a complex mass spectrum due to fragmentation ions, while PIMS clearly revealed the detection of molecular ions of Z56, which is butane, and Z100, which is methyl methacrylate. In our next application, the gas evolution process of zinc acetylacetonate is evaluated using the photoionization mode in STAMS under helium atmosphere. This is the result. Two main evolved gaseous components are observed at 180 degrees centigrade in PI method. One is acetyl-acetone, which is dissociated from the complex. The other is zinc acetylacetonate. As you know, zinc has some isotopes. That's why we can see some peaks from 262 to 266. It is found that the metal itself is evaporated. For those who are interested in the thermal behavior of zinc acetylacetonate under humidity atmosphere, here is a reference material written by Dr. Tadashi Ari and Dr. Akira Kishi. In this paper, data obtained from instruments like STAMS, STA with humidity generator, and XRD-DSC are presented. Please send us a comment requesting for this article so we can send this to you by email. The next application is a result of thermal decomposition of asbestos. When asbestos is being scrapped, the heating and the melting process are indispensable. In this case, the TGMS is very useful for evaluating the detailed reactions. Here, the thermal decomposition of asbestos and chrysotile in the inert atmosphere was evaluated by TGMS. This graph shows the result of STA and MS as a function of temperature. Here, the green curve are TG and derivative TG or DTG curve, and the blue line is DTA. We can see that multiple gases evolved corresponding to the STA curve. In the next few slides, we will be analyzing this data. Now let's focus on the colored area around 350 degrees centigrade to 450 degrees centigrade. The evolution of carbon dioxide is confirmed by the detected MS ions corresponding to 1.12% mass loss. The release of carbon dioxide from magnesite is speculated through the reaction shown on the slide, where magnesium oxide is formed while carbon dioxide is evolved. Now let's move on to the higher temperature, which is around 500 degrees centigrade up to 700 degrees centigrade, highlighted on the colored area. Here, about 12% mass loss is observed in TG associated with endothermic reaction. The evolution of water is confirmed by the detected MS ions. The release of water from chrysotile is speculated by the following reaction shown on the slide, where phosphorite is formed during the dehydration process. Finally, we analyze the colored area around 830 degrees centigrade. The exothermic peak due to recrystallization of phosphorite is confirmed in the DTA curve. Through these, we were able to analyze the thermal decomposition behavior of asbestos in a detailed manner by using TGMS. These are our available products in thermal analysis. Today, I have discussed with you STA8122, where you can measure from room temperature up to 1500 degrees centigrade. DSC Vesta, where you can measure from minus 170 degrees centigrade up to 725 degrees centigrade, depending on the cooling option. And Evolved Gas Analysis System with a commercial name Thermomass Photo, where you can measure up to 1000 degrees centigrade, equipped with a skimmer type interface and with electron ionization and photo ionization techniques available as a standard. Other products such as TMA 8311 as well as other hyphenated techniques in Evolved Gas Analysis and XRD-DSC are also available. All these systems have a wide range of options that will provide solutions to your needs. We provide not only lectures and hands-on training sessions, but also live demonstrations on your samples for free. If you have some inquiries, you can send us an email on the email address provided in the slide. Thank you for your interest and for attending this webinar. We hope to see you again in our future sessions.